So today, as we look at arithmetic sequences, I'm going to use a couple of examples from your textbook. So if you'd like to follow along with that, if you can see here, it says 5-57. So that means from this section, so 5.2.2, you'll find a problem here labeled 5-57. That's the one we're working with, so you know where to look at in the future. All right, here we go. So we've talked about what a term is. So the terms of a sequence are simply the numbers in the sequence, and they're ordered. So the first number is the first term. The fourth number is the fourth term. The term number, so for this, it's 1, 2, 3, 4, 5. It's just counting the position in the sequence. All right, so this particular sequence, we are asked to tell, is it arithmetic, geometric, or neither? So let's check. I like to check arithmetic. Well, let's just look at it first. I notice it goes from negatives to positives. Now, right away, we should know that's not going to be geometric. Geometric, you either keep the sign the same the whole time, or you switch back and forth between positives and negatives. So this can't be geometric. Instead, let's check to see if it's arithmetic. So from -9 to -5, that went up by 4. From -5 to -1, that goes up by 4. -1 to 3 goes up by 4. 3 to 7 goes up by 4. Yeah, okay, this is going to be arithmetic. And how do we know? There is a common difference of 4. Another way to say that would be to say, to get from term to term, you add 4 each time. And that's what makes the sequence arithmetic. Now, the next one's not a trick. It's simply asking, what is the first term of the sequence? So you look at your list and see what number's in front. It's -9. And if they had asked, what is the third term? You'd count to the third number. You'd say the third term is -1. Please don't make that complicated. So next up, when the sequence generator, so that's just referring to the pattern of the sequence, adds a number to each term, okay, that value is known as the common difference. All right, well, in this case, we found that. It's 4. If it is the difference between the term and 4, okay, there we go. So our sequence generator this time is to add 4. So that's the pattern for the sequence. We're adding 4 each time. That's our common difference. Now, you should know, we're going to use the letter D to represent that common difference, a lowercase d. So when you see that, it is referring to the common difference from the arithmetic sequence. Next up, record the sequence in a table. All right, now this is a notation that your book here likes to use, and so we're going to use it as well, so you're familiar with it. When you make your table, the first column is always going to be the number of the term. So we've got 1, 2, 3, 4, 5 numbers. So we're going to have 1, 2, 3, 4, 5 n's. So the number of the term, we use the letter n. That's your input column. So that's like the x's. Now the second column, that's the value of the numbers in the sequence. And I'm going to call that t of n, because your textbook is going to call that t of n. Now this is function notation, so the t is just the name of the function, and n is telling us what number goes in. So for the first term, you're actually evaluating t of 1. That just means what is the first number in the list, and it ended up being -9. The second number in the list was -5, then -1, 3, and 7. So in table form, it's just the same numbers listed top to bottom, but off to the side, you list the number of the terms, so first, second, third, fourth, and fifth. So it says, remember, a sequence table compares the term number n. I'm going to make a note here. That's our input. And the value of each term, t of n, which is the output. So when someone gives us a term number, we tell them what the value of the term in the sequence is. So next up, graph the sequence. So to graph it, I'm actually trying to decide if I want to do it by hand or use Desmos. I think I'm going to use Desmos just because it's going to make a more accurate graph. So to do that, it's just a table of numbers. So to our Desmos, let's insert a table. These are my n's and my t of n's. So we had 1, 2, 3, 4, 5 terms. The terms were -9. Whoops. There we go. Oh, it won't let me put that in there. I'm going to have to just call it t. So you notice it gave a little exclamation point. That's what Desmos does when it doesn't understand something. So it says too many variables. Try just using t. So we're just going to use t. It's still going to mean the same thing. It's important for you to know that. Okay, so the first term, -9, -5, -1, 3, and 7. I'm going to make it a color that's a little easier to see. And then to get a nicer picture, I'm going to click the little magnifying glass. Now, even though I'm making one here, I want you to make one yourself. Practice entering this into the Desmos and make sure that when you click the magnifying glass, your graph ends up looking like my graph. So we should see these points going along. Notice they kind of look like they're in a straight line pattern, don't they? That's what it looks like to me anyway. Okay, back now to our question. So graph the sequence. We did that. Now, should the graph be continuous or discrete? Here's what that means. So a continuous graph is going to be like a whole line. That's a continuous graph. It doesn't have any breaks. It doesn't have any separations. It's all connected. A discrete graph means that your points are often separated. So a single point here, a single point here, a single point here. This is a discrete graph. This is a continuous graph. Which did we have? We had a discrete graph. Now, I hope that makes sense. When we're thinking about here our inputs and outputs, you can have the first term in a sequence. You can have the second term. But you're not going to have a 1.78 term. That just doesn't make any sense. We're counting things. It's going to be measured in whole numbers. So that means our inputs are going to be separate. Therefore, the points on our graph are also going to be separate. How is the common difference related to this graph, and why does this make sense? Well, what was our common difference? It was 4. So as I'm looking along here, so each time, so let's count my boxes. So each box here to the side is going by 1. But notice here vertically, each little division is counting by 1. So tell you what, I'm actually going to go back to a standard zoom here. So we're using the same scale. And I'm going to switch to my presentation view. Okay. Now, each line represents 1. So 1, 2, 3, 4, 5 down, 1, 2, 3, 4, 5 across. To get from this point to this point, I moved over 1, but up 4. Over 1, up 4. Over 1, up 4. Think about that. Doesn't that kind of look like a slope triangle? I'm going to put it this way as we come back here. How is the common difference related to the graph? The common difference, which remember we're going to denote using the letter D, lowercase d, as I try and get this to be a pen again. I'm trying fairly desperately. All right, let's go now back to pen, see if that makes a difference. All right, we'll try and type it instead. So the common difference D gives the rate of change of the graph. That's how I'm going to describe it. So if the common difference is 4, then that means every time you move 1 spot down the line to the next term, you're going to go up 4 spots. If the common difference were different, if it were a different sequence, and we had a common difference of, say, -2, then every time you move 1 spot to the right, our graph would end up going down 2 spots. Now, next up, we're going to write an equation to model the sequence. Begin with t of n equals. Okay. I do need you to know there are a couple different ways this equation may look, and I know that can be confusing. If you base it on the first term, it's going to look like this. T of n equals your first term, T1, plus the common difference times n minus 1. Now there's a second version that's the same thing, but it's based on the 0th term. And it looks like this. You start here with T0, and then you just add on d times n. Now, we're going to start with this one because that's what we have. We have the first term. We'll talk more about this in the future. I just want you to know this exists because we are going to see it later on. So to write an equation for this, we're going to start with t of n, leave those as letters. But for the first term, actually put in the number that is the first term in our sequence, which for us was -9. Then add on your common difference, which was 4. And then this n minus 1 is also just going to stay as letters. So you're going to put in specific numbers where the boxes are, but leave everything else exactly as it looks. Now, to get to this other version, it's not complicated. You would just say, all right, well, let's take the 4 and distribute it and see what happens. So this is a good equation. I'm actually going to highlight it just to let you know this is perfectly good. But you may also see it written this way. If you distribute the 4, so 4 times n, 4 times -1, and then put the -9 and the -4 together, combining those like terms. This second version is also okay. These are actually the same equation. So if I hop back to Desmos here real quick, if we type t of n equals -9 plus 4 times n minus 1, oh, because I used n's up there and t's, I'm going to have to tell you what, I'm going to get rid of this temporarily. All right, so there's the line that we get. I just want to show you that it's the exact same line as if I would instead say -13 plus 4n. Takes us to the exact same line. Nothing changes there. Just to show that, I wish I could type multiple t of n's, but it won't let me. So I'm going to just do a switch. What we had before was -9 plus 4 n minus 1. Now I switched my letters a little bit. It's important that you know that doesn't really change anything. Notice that these two equations just give you the same thing. Okay, so back now to what we had before. Thank you for your patience as I get Desmos to work with me. Okay. So next up, what is the domain of the sequence that you have written? Now, this is a technical thing. So I'm going to talk now to those of you who are planning to move into IM2, right? So if you're planning to go into IM2, I want you to think about this. Domain just means which inputs. So domain means which inputs can we use? Now, this isn't meant to be tricky. Just think about what our n's are here. We started with 1, and then we did 2, 3, 4, 5, etc., all the way through. So we can use our regular counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and on and on. What we can't use are decimals and fractions. Those just don't make sense in this context. What is the 3/7 term. That doesn't even make any sense. We're not going to use negatives. Having negative terms also doesn't make a whole lot of sense. Believe it or not, though, there is a 0th term that we'll talk about in the next discussion. So which inputs can we use? You can use 0, 1, 2, and on without stopping. But those are the only n's you're allowed to use. Other n's just don't make sense in the context of the problem. Now for letter I, what is t of n if n equals 0? Okay, well, let's take our top equation here for a second and put a 0 in for the n's. Remember, these equations are the same, but I just want you to see what's going to happen. If we put a 0 in for the n in the top equation, t of 0 equals -9 plus 4 times 0 minus 1. Now let's simplify. 0 minus 1 is just -1. 4 times -1, we're doing the order of operations, is -4. And -9 minus 4 is -13. So the answer to the question, what is t of n at n is 0, is -13. Do you see that number showing up right there? Take a look at that second equation form. I told you it's going to start with the value of the 0th term. Well, there it is. It's the 0th term. So how is this represented in the sequence equation? If you leave it in the first form, it's not. You can't see that term anywhere. If you distribute and simplify, it's going to be this constant that's added at the very beginning here, the -13. So that's why sometimes you refer to that 0th term as a starting point, a start value. It does take a little bit of time and practice to get comfortable with the first term and with the 0th term. But if you stick with me, I promise we can get it done.